What if I told you there's this one mathematical tool invented centuries ago that can measure literally everything? I'm talking about the air inside your lungs, all the way to the mind-bending idea of infinity itself. Today, we are unlocking the absolutely surprising power of calculus. Okay, let's just dive right in. Take a look at this shape on the screen. See how it's kind of trapped between those two swooping curves? It's not a square, it's not a triangle, it has no straight sides. So, how in the world would you find its exact area? Seems like a pretty tough puzzle, right? Well, it turns out this challenge isn't tricky at all. Actually, it has an incredibly elegant and powerful solution. And this solution is the key that's going to unlock everything else we talk about today. In fact, once you see the logic behind it, you'll realize that measuring this complex-looking thing is almost as easy as measuring a plain old rectangle.
And here it is, the definite integral. Now, I know it looks a little intimidating with that funky S symbol, but the idea behind it is pure genius. Just think of it as a superpowered tool for adding up an infinite number of impossibly thin little slices of an area. And for our problem, the formula is simple. Just find the area under the top curve and then subtract the area under the bottom curve.
So here's how it works. Calculus lets us find the entire area from that top curve all the way down to the bottom line. Then we just do the same thing for the bottom curve and subtract it. And what are you left with? The exact area of that weird shape we wanted in the first place. It's simple, it's powerful, and it is perfectly precise. Okay, so that's a neat geometry trick. But where does this actually show up in the real world? Well, let's get personal. In fact, let's look inside your own body, at the very air you're breathing right this second. You know, every time you inhale, not all of that air actually gets to your lungs to do the whole oxygen exchange thing. Some of it just hangs out in your airways, your windpipe and all that. It's called respiratory dead space, and measuring it is actually a huge deal for understanding lung health. But how can you possibly measure that? And you guessed it, doctors solve this with calculus. On this graph, you can see what happens when a patient breathes out after taking a big breath of pure oxygen. We track the nitrogen that comes out. That rising curve is the key. By calculating the area between that curve and a straight line, we find the exact volume of that wasted air. Does that look familiar? It's just another area between the curves problem. And by applying that exact same integral formula, doctors get a precise answer. For a typical person, it's about 140 milliliters of each breath. That's a number that's literally impossible to see or measure directly, but calculus finds it. So, we've measured finite shapes, things with clear boundaries. But what happens when a shape doesn't end? What if it just goes on forever? Can calculus still handle that? For this, we need an upgrade. We need what's called an improper integral. A normal, or a proper integral, is for shapes with clear start and end points. But an improper integral? That's what we pull out when one of those boundaries is infinity. And here's where your brain might start to hurt a little. The area of an infinite shape can sometimes be a perfectly finite normal number. Now, this might sound totally abstract, but it has some seriously practical financial uses. Think about a nonprofit, for example. Let's say they want to fund a scholarship that pays out a certain amount of money every single year forever. How much cash do they need in the bank right now to make that happen? Using an improper integral, we can figure out something called the capital value. So if we integrate that perpetual $20,000 a year income stream while also factoring in a 10% interest rate, we find the total value today. The answer? They need a single one-time donation of $200,000 to fund that scholarship forever. We just put a finite price tag on an infinite promise. All right, so we can measure the finite, and we can even put a number on the infinite. Now let's push our tool to its absolute breaking point, where it reveals something that seems to completely defy all logic. I want you to meet Gabriel's horn. You get this shape when you take the simple curve y equals 1 over x and you spin it around the axis. You can see its bell shape gets narrower and narrower and narrower, but it never ever actually closes. It just goes on to infinity. And it's holding a very, very strange secret. Okay, now here's where it gets really weird. Using another improper integral, we can actually prove that the surface area of this horn is infinite. That means if you wanted to paint it, you would literally never finish the job. You would need an infinite amount of paint. So here's the question. Could you fill it with paint? The volume of Gabriel's horn is pi. That's it. A simple, elegant, and very, very finite number.
Just let that sink in for a second. You can't paint the surface because it's infinitely big, but you can fill the entire infinite shape with just about 3 cubic units of paint. It's a perfect paradox, and it's only revealed by calculus.
And this isn't just some weird mathematical party trick. From economics to rocket science, this one idea of integration is absolutely everywhere. It's used to figure out how much value consumers get in a market, the exact speed a rocket needs to escape Earth's gravity, even the chances of things like traffic accidents happening. The applications are, well, they're truly endless. So, we started with a simple little shape and ended up by filling an infinite horn with a finite amount of paint. It just goes to show you that with the right tools, problems that seem impossible are often just waiting for us to look at them in a new way. Which really makes you wonder, what other impossible things are out there, just waiting for us to measure them?